Good day, everyone. This is Math 112, Module 5, Inner Product Spaces. And before we go to our main discussion, I will introduce to you the presenters. Yours truly, CURIBA and James Draven as CRUZ from PCD 06401A. So, our topic for this discussion is under the Module 5, 5.4 Mathematical Modeling and Least-Squares Analysis. So before that, we have to go to the objectives. This is our objectives. Number 1, define the least squares problem. Number 2, find the orthogonal complement of a subspace and the projection of a vector onto a subspace. Number 3, find the 4 fundamental subspaces of a matrix. Number 4, solve a least squares problem. Number 5, use least squares for mathematical modeling. So for the definition, we have to define the least squares problem. So what is the least squares problem? In this section, you will study inconsistent system of the linear equation and learn how to find the best possible solution of such a system. The necessity of solving inconsistent system arises in the computation of least squares regression lines. So for the least squares problem, given an m by n matrix A and a vector V in R to the n power, the least squares problem is to find the x in R to the n power such that the norm of ax minus b squares is minimized. The necessity of solving inconsistent system arises in the computation of least squares regression line as this illustrated in our example number 1. So we have here let 1 and 0, 2 and 1, and 3 and 3 be 3 points in R squared. As shown in figure 5.22, how can you find the line of y equal to c sub 0 plus c sub 1x that best fits these points? So for our solution, so this is the figure 5.22 where it is already given. But we have to know what is this line and if this is collinear to the points given. So one way is to note that if the 3 points were collinear, then the following system of equation would be consistent. So this is our equation. So after we write this system of equation, we have to know if this system is consistent. So this system can be written in the matrix form of AX is equal to B, where we have here in RA, we have 3 by 2 matrix. So we have for the row 1, 1, 1, and 1. And for the row 2, where we have 1, 2, and 3. So for the V, we have 3 by 1 matrix. So we have 0, 1, 3. And for our X value, we have C sub 0 and C sub 1, where it is 2 by 1 matrix. So after we written it as a matrix form, because the points are not collinear, however, the system is inconsistent. Meaning of inconsistent, it has no solution. Although it is impossible to find x such that ax is equal to b, we can look for an x that minimizes the norm of the error of ax minus b. So the solution of x is equal to C sub 0, C sub 1 transpose of the minimization problem is called the least squares regression line. Y is equal to C sub 0 plus C sub 1x. So we have here another solution or another example to find if the line best fits the points. So this is under example 2. So I'm sorry for that. Let negative 1, 1, 1 and negative 1, and 3 and negative 3 be 3 points of r squared. How can you find the line y is equal to c sub 0 plus c sub 1x that best fits these points? So first, we have to identify the following system of equation to know if it would be consistent. So this is our following system of equation. C sub 0 minus C sub 1 is equal to 1. C sub 0 plus C sub 1 is equal to negative 1. C sub 0 plus 3 C sub 1 is equal to negative 3. So this system can be written in the matrix form. AX is equal to B, where RA. So I'm sorry earlier I did not explain the value of C sub 0, where C sub 0 is equal to 1. It is already equal to 1 and it is already fixed. So here on our matrix form, our value of A, we have here 3 by 2, where we have 1, 1 and 1, negative 1, 1, 3. So for the value of B, we have here 3 by 1 matrix, 1, negative 1, negative 3. So for the value of X, we have here 2 by 1 matrix, C sub 0, and C sub 1. So for the formula, we can now have multiply AX if it is equal to B. But we have here the formula of X is equal to transpose A, or we are calling this turf. We can call this turf if it is connected to orthogonal complement of W of A. So we have this formula where the inverse of A transpose A, the inverse of transpose A times transpose A times A. So first we have to find the transpose A and A, where the transpose of the value of A from 3 by 2, it will be 2 by 3. So that is the transpose value of A. So the transpose value of A is 1, 1, 1, negative 1, 1, 3 by 2 by 3 matrix. So for the A, we just copied the value of A by 2 by 3 by 2 matrix, 1, 1, 1, negative 1, 1, 1. So we are going to multiply this and it will be equal to 2 by 2, where the value of 2 by 2 matrix is 3, 3, 3, 11. So now we are going to find the inverse of A sub transpose A times A. So the value of our A transpose A times A is 3, 3, 3, 11, where it is 2 by 2 matrix. So for the transpose, for the inverse of this value, it will be equal to, again, it will be 2 by 2 matrix. However, the value will be inverse. So the inverse value is 11 over 24, negative 1 over 8, negative 1 over 8, and 1 over 8. So we are going to apply in the formula this thing that we first find for substitution. Inverse of transpose A times A is 11 over 24, negative 1 over 8, negative 1 over 8, 1 over 8 times the transpose A times A, where A, where it is equal to 1, 1, 1, negative 1, 1, 3. And also we are going to multiply it by our value of B, where we have the value B 1, negative 1, negative 3. And after the multiplication, we are going to find the answer of x, where our c sub 0 is equal to 0 and c sub 1 is equal to negative 1. So this is the line of y equal to sub 0, c sub 0 plus c sub 1 x. So for the value of slope, we have the value of 0, and for the intersection, we have negative 1. So y equal to c sub 0 plus c sub 1x will be equal to y equal to negative x, where if we are going to use the GeoGebra, and if we are going to point all the 3 points of r squared, and then enter the value of our line, it will be exact as the point. So this means that this is the best fits for these points, and this is collinear and consistent because it has a solution. So that is for our least squares regression lines. For the orthogonal complement, the orthogonal complement of the trivial subspace 0 is all for r to the n power, and conversely, the orthogonal complement of r to the n power is the trivial subspace of 0. You can find the orthogonal complement of subspace of r to the n power by finding the null space of a matrix. So for the definition of orthogonal complement, if S is a subspace of r to the n power, the orthogonal complement of S is the set S-terp, where S-terp is denoted as orthogonal complement of subspace S is equal to U, where U is an element for r to the n power, where B times U is equal to 0 for all vectors of B is an element for S. So we have here example number 3, finding the orthogonal complement. Find the orthogonal complement of the subspace S for R to the fourth power spanned by the two-column vector B1, B sub 1, and B sub 2 of a matrix A. So our matrix A is equal to, for the V1, we have the value of 1, 2, 1, 0. For the B sub 2 is 0, 0, 0, 1. So for this solution, S-terp is equal to U, as U is an element for R to the fourth power, where V times U is equal to 0. So here we need to find the transpose A U is equal to 0. So for the matrix A, we already transpose it. We have now 2 by 4 matrix, 2, 1, 2, 1, 2, 1, 0, 0, 0, 1 times to the x sub 1, x sub 2, x sub 3, x sub 4, where it is equivalent to U and equal to 0. So for the S term is in the null space of transpose A, where the value of transpose A is negative is 1 to 1 0 0 0 1, and then we are going to find the null space where our from our transpose A for the value of U for our x sub 1, it is x sub 1 is equal to 2 x sub 1 minus x sub 1 plus 2 x sub 2 ma x sub 2 plus x sub 3, then plus x sub 3. And then here, we are going to transpose the value of 2x sub 2 plus x sub 1 in order to get the value of x sub 1. So we now have x sub 1 is equal to negative 2, where we let x sub 2 be equal to s, and then x sub 3 be equal to t, where x sub 2 and x sub 3 is the independent variable. So negative 2s minus t, where our x sub 2 value is s and x sub 3 value is t, and for x sub 4 value is equal to 0. So we need to get the value of s, where in our x sub 1 we have the value of negative 2, for x sub 2 we have 1, and then for the x sub 3 and x sub 0, x sub 4 we have the value of zeros. So plus to the t value, we have negative 1, and then in x sub 1, then for x sub 2 we have 0, in x sub 3 we have 1, and then for x sub 4 we have 0. So now this is the basis for the orthogonal complement of the spaces, orthogonal complement for the subspace S. It is equal to negative 2 1 0 0, and then negative 1 0 1 0. For the direct sum, the definition of direct sum, let S sub 1 and S sub 2 be two subspaces of R to the n power if each vector x is an element of R to the n power, can be uniquely written as a sum of a vector S sub 1 from subspaces of sub 1 and a vector of S sub 2 from subspaces of sub 2, S sub 2, and x is equal to S sub 1 plus S sub 2, then R to the n power is the direct sum of S sub 1 and S sub 2, and you can write S to the n power is equal to S sub 1 O plus S sub 2. So this is the direct sum. So for example number 4, for direct sum, this is from the example number 2. You can see that R to the R cube is the direct sum of the subspaces. S sub 1 is equal to span 1 0 1 1 1 0, and then S sub 2 is equal to span negative 1 1 1. So because for the vector 1 of S sub 1 is equal, for the vector 1 of S sub 1 multiplied by the S sub 2 is equal to 0, and for the vector 2 of S sub 1 and multiplied in S sub 2 is equal to 0. Therefore, it is direct. So for the subspaces of example number 2 it is equal. So for the example number 3, you can see that r to the fourth power is equal to s direct sum orthogonal complement of subspaces S, where for the S value we we multiply and add this both, and it is equal also for 0. Projection onto a subspace. We have here theorem 5.14, the projection onto a subspace, where if the term of sequence are designated as u sub 1, comma u sub 2 up to u sub t is an orthonormal basis for the subspace S of R to the n power, and V is an element for R is an element of R to the n power. Then the projection of vector V onto S, where it is equal to V times u sub 1 times u sub 1 plus V times u sub 2 times u sub 2 up to V times u sub t times u sub t. So here for our example number 5, the projection onto a subspace, we have to find the projection of a vector V, where the value of V is 1, 1, 3, onto the subspace S of R cubed spanned by vector W sub 1, where it is equal to 0, 3, 0, and W sub 2, where it is equal to 2, 0, 0. So we have here example number 6 for fundamental subspaces. We need to find the 4 fundamental subspaces of a matrix A is equal to 1, 0, 0, 0, 1, 0, 0, 0, 2, 0, 0, 0, 0, 1, 0, 0. So for the solution, for the column space of A is equal to the span of 1, 0, 0, 0, 0, 1, 0, 0. So here we only get the value for the first and third column. So for the R, or the column space of transpose A, is equal to 1, 2, 0, and comma 0, 0, 1. So here we get it by R cubed, where the only value for the matrix A has 1, 0, 1, 2, 0, 0, 0, 1 equal to 0, 0, 2 for the R squared, R cubed. So here we transpose the first, second, third row, and then get the first and second value of the transposed column. So it is equal to span 1, 2, 0, comma 0, 0, 2. So for the null space of A, it is equal to span negative 2, 1, 0, where negative 2 get negative 2 is from the substitution for from x sub 2 into the equation 1 to find the x sub 1. So for the value of x sub 1, 0, 0 minus 2 times 1 minus 0 times 0. And then it is equal to negative 2. So to get also the another idea in our matrix A, we just need to get the value of x sub 1, where x sub 1 plus 2 x sub 2 is equal to 0. Then x sub 1 is equal to negative 2 x sub 2. So for the value of x sub 2, we can enter any other non-zero value. So here we put the value of 1, and then for the x sub 3, it is equal to 0. So there you go. The null space of A is equal to span negative 2, 1, 0. So to get the null space of transpose A, we need to transpose our A from 2 by 3 matrix into 3 by 5 matrix. Therefore it is already augmented. So by Gauss-Jordan elimination, we get the value of 1 0 0 0 0 1 0 0 0 0 0 0 0 0 0 0 0 0. And then the value of null space transpose A is equal to span 0 0 1 0 and 0 0 0 1. So this is the subspace of R to the 4th power. So we have here other properties of the 4 fundamental subspace, the theorem 5.16, the fundamental subspace of matrix. If A is an M by N matrix, then number 1, column space of A and null space of transpose A are orthogonal subspace of R to the M power. Then number 2, column space of transpose A and null space of A are orthogonal subspace of R to the N power. And then for our number 3, R or column space of A is direct sum of null space of transpose A is equal to R to the M power. And for the last one, number 4, column space of transpose A is direct sum of null space of A is equal to dr is equal to R to the N power. So this is the end of my report. And then we are going to the next reporter where my partner James Draven Cruz will be reporting.
So hello everyone. After our first reporter a while ago, we'll be now proceeding to solving the least squares problem. So here, after that discussion, we assume that we understand all of that information because we will use that enable for us to solve this problem. So now we have provided some examples about the least squares problems or about the solving the least square problem. So we have here our example number 1, which is the A equals the column 1, which is the 2 1 1, column 2, which is the 1 2 1, and as for our B, which is equal to 1 0 and negative 3. So the first thing that we need to do is to first verify if there is no solution to the AX equals B. So afterwards we will write the augmented matrix. So here for our augmented matrix, we will write it, so it means that our A and also our B will be put together. So from our A to 1 1 and 1 to 1, and for our B is 2 or negative. So using the raw echelon form, so the first column will be the coefficient of x, and the second column will be our coefficient of x up to, and column 3 would be our constant. So now since we have a contradiction in row 3 that the 0 is equal to 1, which is not true, which verifies that the equation ax equals b has no solution. Now since we find our A transpose A, or we will be now getting our A transpose times A as well as our A transpose times B. So our A transpose is row 1, which is the 2 1 1, and row 2, which is the 1 2 1. Since we are getting our transpose or A transpose, when we are talking about the transpose, it means our row to column will be switched from one another and vice versa. So since our A is column 1 2 1 1 and column 2 is 1 2 1, it would be row 1 2 1 1 and row 2 is 1 2 1. So afterwards we will just simply multiply this given matrices or vectors, which is the A transpose as well multiplied to A. So it would be 2 times 2 plus 1 times 1 plus 1 times 1 equals 6. And 2 times 1 plus 1 times 2 plus 1 times 1, which is equals to 5. And as for our A column 2 row 1, column 2 row 1, 1 times 2 plus 2 times 1 plus 1 times 1, which equals to 5. And for our last row and column, we have here 1 times 1 plus 2 times 2 plus 1 times 1, which equals to 6. So for our next step, we're gonna find the A transpose times B. So since we already have our A transpose, which is the 2 1 1 and 1 2 1, we will just simply multiply it by our B, which is the 2 0 negative 3. So after we multiply that to given, we will be able to get the 1 and negative 1. Since we've already got our A transpose times A as well as our A transpose times B, we're gonna be solving about the system A transpose times AX equals A transpose B. So as you can see here, we have our data, which is the 6 5 5 6, as well as the positive 1 and negative 1. So next we will write the corresponding augmented matrix and write the augmented matrix in reduced raw echelon form. So I guess that all of us are familiar or know how this reduced raw echelon form works. So from 6 5 5 6, we put all together it by our 1 and negative 1. And we are aiming from this 6 5 1 and 5 6 negative 1 to be a 1 0 1 and 0 1 negative 1 data. So enable for us to do that, we need to do and follow the steps of reduced raw echelon form, which is we need to first see the row 1. So from 6 we need to make it 1, so we need to divide it by itself. So r1 equals r1 over 6, so 6 divided by 6 equals 1. As well as for our r1, we also need to make this 5 and 1 to be divided by 6. So R1 divided by 6, which is 5 divided by 6 equals 5 over 6. And 1 divided by 6 equals 1 over 6. So the same for our row 2. We have here our formula R2 minus 5 times R1. Since we are aiming to get the 0 from 5 and also the 1 from 6, as well as for our negative 1. So we have here 0, 11 over 6 and negative 11 over 6. And as for also our row 2 again, since we are aiming for the 5 and 1 to be 0 and 1, we just need to follow the formula we that we use, which is the R2 equals 6 times R2 over 11. So it will be 0, 1, and negative 1. The same as for our R1. That we need to R1 minus 5 times R2 over 6. That's why we get this row 1, 1, 0, 1, and row 2 is 0, 1, negative 1. So as for our next step about these least square problems, we are now getting the A transpose times B, which we have here our A transpose, which is the column 1, 2, 1, 1, and column 2, which is the 1, 2, 1. We will just need to multiply it to our B, which is the 2, 0, and negative 3. That's why we got that 1, negative 1, and negative 2. So next, we can determine this by determining the magnitude of the differences of the vector b and the vector resulting to the vector ax. So we have here b minus ax. So we have here our 2, 0, negative 3. We just need to subtract it by 1, negative 1, and negative 2. That's why we get the 1, 1, negative 1. So after that, we will just simply square the answer that we got. So it will be square root of 1 times squared plus 1 times squared plus negative 1 times squared. That's why we got this square root of 3. So as we analyze these answers, we can see that the 1, negative 1, and negative 2, which is our b, is not equal to negative 2, 0, and negative 3. So this just indicates that the vector 1, negative 1, and negative 2 is square root of 3 units from the vector 2, 0, negative 3. So as for our example number 2, still about the least squares or solving least squares problem, we have here our given A, column 1 equals 1, 1, 0, 1, and column 2 negative 1, 1, 1, 0, and 1, 1, 1, 1. So we just need to repeat the steps that we did a while ago. So we have here also our B, which equals to 2, 1, 0, 2. So first, we also need to first verify if there is no solution to our ax minus b. So since there is no solution to this problem, we just need to write the augmented matrix again. That's why it leads to this given. So as you can see, we need to do again and find out our A transpose times A as well as our A transpose times B. So as for our A transpose, we just need again to switch or swap the row from row to column and vice versa. So we have here this given. So since we got the given, we just need to do the Gaussian elimination in able for us to get the answer from the A transpose times A. So we have here our 3, 0, 3, 0, negative 1, 1, and 3, 1, 4. So here we're gonna find now our A transpose times B. So A transpose times B, we just simply multiply it to our B, our A transpose, which leads to our um, row 1, which is 1 times 2 plus 1 times 1 plus 0 times 0 plus 1 times 2, which equals to 5. So as for our row 2, we have here negative 1 times 2 plus positive 1 times 1 plus 1 times 0, as well as 0 times 2, which equals to negative 1. The same as for our row 3, which is 1 times 2 plus 1 times 1 plus 1 times 0 plus 1 times 2, which equals to 5. So since now we're gonna be multiplying the 1101, negative 1110, 1111 to 5, negative 1, 5, we will be able to get this, the 10, 9, 4, and 10. So afterwards, we're gonna be determining the magnitude of differences of vector 3 and the vector resulting to vector ax. So b minus ax, so we have here our 2, 1, 0, 2 minus 2, the product that we got from earlier, which is the 10, 9, 4, 10. So it is equal to negative 8, negative 8, negative 4, and negative 8 also. So afterwards, we're gonna be squaring this answer. So from that, it will be square root of negative 8 times squared plus negative 8 times squared plus negative 4 times squared plus negative 8 times squared equals to square root of 208. So after those computation, it indicates that the vector 10, 9, 4, 10 is square root of 208 units from the vector 5, negative 1, 5. So next here, as for our next example, which is about the normal equation, we have here, we provided some example from the book that we have given to us by Mom Liberty. So we have here our given 3 points, which is the 2 comma 1, 1 comma 2, and 1 comma 1. So our A would be the column 1, 1, 1, 1, and the column 2, 2, 1, 1. So our Y would be the 1, 2, and 1. So in our system of equation, we're trying to fit the line y equals b naught plus b1x through these 3 points. So there are 3 equations and there are only 2 dimensions. The points are not collinear, so there is no solution. So it was said that our y is only our y and our x is not matched, or its dimension is unmatched. That's why we can say that this so afterwards we're gonna be solving, and we're gonna be form the normal equation. So here we're gonna be providing the A transpose times A. So when we say all again transpose, we switch from row to column and vice versa. So from 1, 1, 1, column 1, and column 2, 2, 1, 1, to A transpose, it would be row 1, 1, 1, 1, and row 2, 2, 1, 1. So we will just multiply it by the A, which is column 1, 1, 1, 1, and 2, 1, 1. So after that, we also get the A transpose and multiply it also to our Y, which is the 1, 2, 1. So we have here the product after multiplying the A transpose to A, which is we get the 6 and 5. So this is already a solvable dimension because we already have balanced dimension here. So we have two equations and two unknown. So using Gaussian elimination, I know that all of us are familiar with this. So we will able to determine both x and y. So here we have here our given. We just need to make it to row 1. We need to make it like 1 and 0, and for our row 2 we need to make it 0 and 1. So enable for us to do that, we need to make some formula in each row. So for our row 1, we have here r1 divided by 3. So 3 divided by 3 equals 1. So that's what we are aiming for. So as well as for our 4, we need to divide our 4 divided by 3 is equal to 4 over 3, and so on and so forth. So for our also row 2, we have here our formula r2 minus 4r1. So for our r2, we have here 4 minus 4 times 1. So we have here 0 and 2 over 3 and negative 1 over 3. So after that, we will be able to make it like 1, 0, and 0, 1 as we can see here in our solution. So our x sub 1 would be 2, and our x sub, and as for our x sub 2 will be equal to negative 0.5. So we didn't forget about our b beta, which is equal to 2 comma r, and b1 is equal to negative 0.5. So our y will be equal to 2 minus 0.5x. So here we gonna proceed about solving or finding the squares regression line. So we have here our example 3 points, which is the negative 1 comma 1 and negative 1 comma 0 and 3 comma negative 3. So for our y, it will be negative 1, 1, and 3, and for x, and for our y, it will be 1, 0, negative 3. So for our small data set, we need to calculate this least squares regression line. So we have here formula r times s1 over sx, and for our beta is equal to the y mean minus b1x mean. So here we have here our sample, computing sample standard deviation. So we need to get this. So in order for us to get this, we need to sum up all of our x's. So we have here 3 over 3 because that 3 is from the n, or the number of our data, which is x. So 3 over 3 equals 1. So our sample means is 1. So for the next step, we need to x minus the n. So it would be negative 1 minus 3. It should be negative 4. And 1 minus 3 equals negative 2. And 3 minus 3 equals 0. And as for our step 3, we have here, we need to square the product that, or the differences that we got. So negative 2 times squared equals 4, and negative 3 times squared equals 9, and 0 times 0 equals 0 still. So for next step, which is the step 4, we have here, we need to sum up all of the products that we got earlier, which is the 4 plus 9 plus 0, which is equal to 13. So For the next step, which is step 5, we have here 13 over 3 minus 1. The 13, that is the sum that we got, and 3 minus 1 is from the formula that we have. So it will be 13 over 2, which is equal to 6.5. Then for our step 6, we have here square root of 6.5, which is equal to 2.550. Since we have done our step 6, which is the square root of 6.5, we're now proceeding to our calculation of correlation coefficient. So for our calculation, we need the x mean, so it must be negative 1 plus 1 plus 3 over 3, that is equal to 1. So our also mean of y, so 1 plus 0 plus negative 3 over 3 is equal to negative 0.6667. So we have here our example. We just need to subtract the x1 to the mean of x, then we need to square it. So it will be negative 1 minus 1 squared plus negative 1 minus 1 squared plus 3 minus 1 times squared equals 8. So this process will be just repeated to the y. So after that, we just need to multiply the differences between the x I minus x mean to the y. So it would be, the answer is negative 8. So as we can see here to our solution, we found out that the x of x and y is equal to negative 8 over 3 minus 1 is equal to negative 4. So in able for us to find the radius or the r, we need to use the solution or the formula xi minus x mean times yi minus the y mean all over square root of the xi also minus x mean times squared, and the element all element of y minus mean y times squared. So after that, we need to substitute the given that we have. So it will be r is equal to negative 8 all over square root of 8 times 8.6667 is equal to negative 0.9608. So for our b1, we need able for us to get those, we need to multiply our radius to sy over sx. So b1 will be equal to 0.9608 times 4.950 divided by 2.550 will be equal to 1.865 or 1.9. It can be 1.87 or 1.9 in 10 decimal places or 100 decimal places. So our beta will be y mean minus b1x equal b1x. So as for our y cone, it would be equal to 1.2333 plus 1.9x. That is our least LSRR. So for the next one, we have here our least squares quadratic polynomial. So we need to find this squares quadratic polynomial. We have already given here 0, 0, 2, 2, 3, 6, and 4, 12. So basically, we have here our guidelines enable for us to solve this easily. So for our data, since we have our 4 points, so our n is equal to 4. So we just need to sum all our x's. So we have here 0 plus 2 plus 3 plus 4 equals 9. That's our column 2 and row 2 first given. So we need to also summarize all our x squareds. So it would be x 0 plus 4 plus 9 plus 16 equals 29. So that's our column 3 third first group and row 3 first given. So sum again all our x cubed. We can get 0 plus 8 plus 27 plus 48. We can get 83, which is our column 3 row 2 and our row 2 column 2. So next, we have here our sum of our x to the 4th powers. and it would be equal to 0 plus 16 plus 81 plus 256, which is equal to 353, which is our row 3 column 3 given. So after that we need to sum of all of our y's, which is equal to 0 plus 3 plus 6 plus 12, which is equal to 20. So from those sums, we need to multiply the y and x. That's why we get 70. And we need to sum all of our y's, and we need to multiply this x squared. Then we will get the 254. So above all that, basically we need to make this easily understand, we just need to multiply all the data that we got, or we're gonna put it in a matrix vertices and multiply it to 20, 70, and 254. That's what we got from our y. So it would be equal to that given from our solution. So here, as you can see. So next we have here our orthogonal projection onto a subspace. So we have here our given B equals 1, 1, 3, and our A 0, 3, 1, 1, 0, 0 spaces. So enable for us to find the orthogonal projection of B and as well as S, we need to solve the D squared problem, which is AX equals B. So like in our examples, we also need to calculate the matrix products, the matrix products A transpose A and A transpose B. So we have here from our transpose times A, our transpose from column to row, switch it, vice versa. We have 0, 2, 3, 0, 1, 0, multiply to A, which is 0, 3, 1, and 2, 0, 0. We have here 10, 0, 0, 4. So this is just a simply multiplication. If we are familiar with multiplying matrices, we'll be able to get it. So A transpose B also, we need to get it. A 0, 1, 3, 0, 1, 0 multiplied by 1, 1, 3, we got 6 and 1. So the normal equations here that we got is, or are, a 10, 0, 0, 4, and 6, 2. We need to multiply again, and using the Gaussian elimination, we'll be able to make the 1004 into 1001 to make it perfect. So enable for us to do that, we need to make our R1 equal to R1 over 10. So it would be 1, 0, 0, 4, and 0 0.6 and 2. For our row 2, we need to use the formula R2 over 4. So it would be 1001, 0 0.6, and 0.1. So we have here our answer. We just need to be what do you call it? We need to be careful about multiplying the given, the A transpose as well as the given A. So finally we have here now the projection of B onto S. So our AX will be equal to 0, 3, 1 and 2, 0, 0 multiplied to 3 over 5 and 1 over 2 that we got from earlier. So it will be equal to 1, 9 over 5, 3 over 5. So we just need to multiply this and add this. That's why we got the 1 over 9 over 5, 3 over 5. And as for our mathematical modeling, so hindi natin kailangan ito pahabain. We just need to analyze the given information or given data from the PPT or PowerPoint presentation that we have. Let x equals 5 because we have, the data represents the 1985. So y is equal to 0 beta times plus c1x plus c sub 2 x squared. So for the data end, we use the model to to estimate the population for year 2015. So we just need to get the data into a data points or set of points, and um, we need to also square our axis. That's why we got that 5, 10, 15, 20, 25, 30 sequence. And also we need to cube our C. We need to square that. That's why we square it rather. That's why we get 25 100 to 95 400 425 and 900 or 625 rather. So here we got that. That's why we need to get the normal equations. So from the presentation or the solution above, we identify or we get the least squares problems. So after that, we will multiply all the information or the data that we got after multiplying the normal equations. We will multiply to our B, which is the 4.9, 5.3, 5.7, 6.1, 6.5, and 6.9 given, which is our population. So afterwards, we will be able now to show our data, which is we have 6 points, so at least square quadratic polynomial model. So our n is equal to 6 since we have 6 data, and we need to sum of all our x's. This is just like what we did the quadratic polynomial that we have earlier. So that's it. Yeah, you just need to be careful in terms of multiplying, putting some square roots as well as cube root until to the 4th power. So we need to also get the y's and multiply it by x, then squared. So after that long solving about all the sums of our x's and y's and the products that we got from x's to multiplying to our x squares, now we have here our x, or we got the value of our c data, c1 and c2, which is 4.5, 0.08, and 0. So evaluating this polynomial at x is equal to 35 gives the estimate of world population for the year 2015. It would be y equals 4.5 plus 0.08 times 35 from our given is equal to 7.3 billion. That's all. So thank you for watching, and I hope you learned something about this lesson. And we just need to a lot of practice or practice exercises that will help us to mold our skills and to learn more about this lesson. More practice would help us to learn more better.